My name is Jagdish Nayak. I am a security applications engineer at TortuaLogic. In this presentation, I will cover how the Radix tool is used to find a security vulnerability on the firmware hardware boundary of an ARM-based SoC. Radix security verification fits into existing pre-silicon verification flows in 4 easy steps. In step 1, the security properties created for the design from the common weakness enumeration database or the security architecture are converted into Radix security rules. Next, in step 2, these security rules are analyzed by Radix to create the security monitor. In step 3, this security monitor is bound to the design and run in the existing verification environment with functional regression tests. The original design or simulation environment is not modified. In step 4, if during the simulation or emulation, the security monitor detects a Radix security rule violation, an error is flagged and debugged using Radix's security debug analysis tools. Radix supports simulation tools and the emulation platforms from Synopsys, Mentor, and Cadence. Let us now look at the SoC design used for this demo. An ARM M3 core is connected to several peripherals and SRAMs via the AHB MUX and AHB to APB bridge. Access to the SRAM2 is as follows. In privileged mode, the ARM core can read and write to the SRAM2. In unprivileged mode, the ARM core must not be allowed to write to the SRAM2. This becomes a security requirement that the SRAM2 protected range must not be written by unprivileged software. Firmware enforces this security requirement by programming the memory protection unit in the ARM core to prevent write requests to the SRAM2 in unprivileged mode. Now let us convert the security requirement to a Radix rule with RTL signals. The write request from the ARM core is tracked when the destination is SRAM2 and is made in unprivileged mode. Such a write request should not assert the write enable for the SRAM2 unless the SRAM2 is not selected. The Radix rule captures the security requirement and tracks whether the write request from the ARM core influences the write enable port of the SRAM2. The Radix rule is easy to write as its syntax is similar to that of an assertion. The Radix rule differs from an assertion in that it tracks all transformations of the write request temporally through various hierarchies in the design, thus making it very efficient and much more powerful than an assertion. The Radix security rule created is used to generate the security monitor. The security monitor is run with the design in a simulation. Next, let us examine the log output of the simulation. When a Radix security rule fails, it displays an error message and the timestamp is displayed in the log file. On a failure, waveform data from the simulation is dumped and analyzed by Radix's security debug analysis tools. On examining the waveform data in Radix's waveform view, the write request from the ARM core is tracked when the address is for the SRAM2 and the request is made in unprivileged mode. This is shown by the red shading on the H-write signal. When the write enable of the SRAM2 gets shaded in red, it means that the unprivileged write request from the ARM core made it to the SRAM and is a security failure. As the protection mechanism was programmed in the memory protection unit, examining the firmware for access privilege to the SRAM2 memory range exposes the bug. The memory protection unit was incorrectly programmed for full access in unprivileged mode. The code is fixed to allow read-only accesses in unprivileged mode to the SRAM2. The security monitor does not have to be recreated as only the firmware is modified and the RTL for the design stays the same. The simulation is now rerun with the fixed firmware. On rerunning the simulation, the rule does not fail. Comparing the waveform views between the failing and passing tests, we can confirm that the firmware fix worked. As seen in the waveform view from the passing test, the memory protection unit correctly blocks the unprivileged write request from the ARM core to the SRAM2. Recapping, the Radix flow fits easily into existing verification environments. The Radix security rule completely captures security requirements. The Radix debug analysis views use information flow tracking to identify the root cause of security vulnerabilities. And finally, Radix detects security violations at the firmware hardware boundary and is more efficient than functional verification tools for performing security verification. For more information, data sheets, white papers, and webinars, please visit the link as shown below. Thank you.